So thank you very much for the invitation. I will talk about avalanches. So we studied avalanches in disordered systems, so mainly on spin glasses, and show you so the results we've got for different systems we studied, and one was specifically with the single spin flip dynamics, and another with the magnetization conserving dynamics. And this is still work in progress. So I will show you how. So our goals, or how we want to answer some questions about the dynamics imposed in a system that might influence the presence or absence of self-organized criticality. But this work was done in collaboration with Helmut Katzgraber, Vladimir Dobrosarlevich, and Gergely Simanyi. So first, so this talk will be a shorter talk than the previous ones, and probably also not so technical. So this first, I will shortly introduce you to the disordered systems we will look at, so the spin glasses, and then I will show you our results in avalanches out of equilibrium in the Edward Anderson model and the spin Sherrington-Kirkpatrick model, which were done with single flip dynamics, and then avalanches. We studied avalanches on the Coulomb glass model, and show you the results here from where the dynamics were different from the previous one. So, and then I will show you put the conclusions and some discussion about for work that we are now doing, and try to understand if or find out if the dynamics imposed into one system might influence scale-free behavior. So first, let's go to the disordered system. So usually we are happy to deal with ordered systems. So if we come to a room which is ordered as this one, so we are happy because we can look and pick a book that we want to read, and it's pretty easy to find straightforward the way we want what we want to pick out. But unfortunately, in real life it's a bit different. So most of the rooms will look probably like this one, and so at the beginning it might be some kind of frustration because we're not able to find any type of order, or but most probably the kid so living in this room will have some type of order that we might not be able to find at first sight. So we want to find some kind of order in the disordered system, and usually these are the systems that we find in nature, so with a more disorder, and usually also show some interesting features. So in the same spirit, I will introduce you first the Ising model. So we are most of us will be familiar with this model. It's a simple model that so here it's defined on a lattice, in this case a square lattice, and on each side there will be a spin that can have a positive or a negative value, and these are coupled via ferromagnetic interactions. So this model has a paramagnetic phase at high temperatures and an ordered ferromagnetic phase at low temperatures. So here we see a plaquette of the Ising model. So the Ising model can be described by this Hamiltonian. So here we have J, the ferromagnetic interaction, and the spins. So in a similar way, the spin glass is defined on a lattice. So in this case, it's again a square lattice, and we have again spins that can point either up or down. But here the big difference is that the spins can be coupled ferromagnetically or anti-ferromagnetically. So we introduce disorder into the system by picking randomly the bonds of the spins. Again, this system has a paramagnetic phase at high temperatures, and at low temperature there's a spin glass phase. So even if we don't see it at first sight, there is some kind of order at low temperatures. So here we see a plaquette of the spin glass model, and it can be described by a similar Hamiltonian than the Ising model. with the difference that here the JIJs are randomly picked. So here is the disorder, and the characteristic of spin glasses is that they have disorder, and from here some frustration arises. So frustration means that here a spin cannot simultaneously satisfy the minimization condition for all neighboring spins. So this spin is a frustrated spin. So the characteristic of spin glasses or glasses in thermal equilibrium are very slow dynamics, and this is due to the complex energy landscape of it. But we are interested in studying these systems out of equilibrium. So, well, it takes quite a long time to reach from a metastable state to a stable state. But we're interested in driving these systems out of equilibrium, and one can do that by applying an external force, and this can be visualized by some kind of tilting of the energy landscape, and thus the configuration at a metastable state becomes unstable and then relapses to the next stable state. So the methods developed for studying spin glasses and also some models of spin glasses have been used, have found wide applications for studying, for example, traffic flow or neural networks. Also some optimization methods have been used for studying the stock market and the Travel-Sexman problem, and also have been used to study power grids. So now we turn to the avalanches. So we are mainly interested in seeing or trying to find out which are the key features of a model that the key feature of a model to display self-organized criticality. So here I give you probably a very sloppy definition from self-organized criticality. So Gunnar gave us a much better one yesterday. But here the important thing is that we can drive a system, we can slowly drive it, and then the system will have fast relaxation events, and these relaxation events can be counted as avalanches, and the distribution of these relaxation events will display a power law distribution, and with a exponential cutoff that scales with the size. And these features are displayed without tuning any parameter, any external parameter. So that's an important feature for self-organized criticality. So self-organized criticality is said to be found in many natural systems, such as earthquakes, solar flares, flow of dislocations. And so it has been interesting to look a bit in more detail why this interesting phenomena emerges. And usually to study this phenomena a bit more in detail, we make use of simple models, so as simple as possible to be able to understand this better. So far, mostly it has been cellular automata models that have been looked at, so probably this is not the best example, as Gunnar told us yesterday, but so this is just for illustration's sake. But we see a small drawback of studying these models because they are not able to really describe physical systems, and they are usually models that are created with ad hoc dynamics to show this behavior. So it's not so easy to understand these models in other contexts. So that's why we turn to spin models that we know that they can describe quite well some interesting physical phenomena, and so we want to look at self-organized criticality in spin models. So far there is one prominent example that has shown to exhibit self-organized criticality. So this was shown by Pasmani and collaborators in 1999. So they looked at the XK model, in presence of an external magnetic field. So, and they found this interesting behavior. So here I show you how they did. So they start with a fully magnetized system. So here we have the system that all spins point in one direction, and this is a fully connected system with random bonds. So here we have the hysteresis loop. So they start with a very strong field. Here's the magnetization, and here we have just a cartoon of the energy landscape and the configuration space.
Is there any relation to real magnets in this model?
To real magnets?
Yeah.
So there are alloys, yeah. So this can describe real.
Is infinite range or
the infinite range? Well, it's still discussed if it's really the mean field can really be applied to finite dimensional. So because there are, for example, if you apply a field there in the infinite dimensional, there's still a spin glass phase, but so far in a finite dimensional, numerically it has not been found. So it's not really known how much from a mean field can be applied to more realistic systems.
But you assume Jij is has infinite range, or?
Yeah, in this case, yes. In this case, yes. So we will then pass to finite dimensional systems.
Okay.
So that's why here we have a fully connected system. So so they changed the external magnetic field just by amount that destabilize one spin, and this spin can trigger an avalanche of other spins, and this is recorded. The statistic of this is recorded, and then the configuration will jump into the next stable metastable configuration. This is done along the whole hysteresis line until all spins are pointing in the opposite direction. So, and when studying at this statistic, at the avalanche of statistics, they have seen self-organized criticality. They have seen a power law distribution. So we here reproduce their results for some a bit larger system sizes than back then. So here we see the distribution of these are spin flips of avalanches along the whole hysteresis line. And we see clear power law with the exponential cutoff for different system sizes. And they found, so back then Pasmandiet and collaborators estimated the critical exponents and made also some data collapse, but we here are going to show the self-organized criticality, but here we will also look at it a bit different. We here define a characteristic avalanche size, n star, which is done by fitting the exponential cutoff with this function, and the characteristic avalanche size will be the constant decay of the fit. So for each system size, we will have one so-called characteristic avalanche size, and we see, and we want to see how these avalanches behaves in the thermodynamic limit. So what we will get if we extrapolate this avalanche size, the characteristic avalanche size. So here I show you the plot of 1 over n star, so the previously defined, as a function of 1 over the size. And here we see that in this case, it's not surprising that we find infinite avalanches in the thermodynamic limit, meaning that there is a scale-free behavior as expected.
So this is recent, or is from
This is with our data. So this we did with our data, but
how does it compare with the previous?
Yes.
This confirms the previous work.
Sorry.
How does it compare with the work of the old work of Simani?
Well, they found also some scale-free avalanches.
It confirms.
Yes, of course. Yeah. So we find, so we just reproduce it and analyze the data a bit different, but get the same results.
So you have now a system.
We have, yeah. So our systems are 10 times larger than the ones studied before. So similar results are found when looking at the magnetization jumps. So so far so good. So now we are interested in the other finite dimensional models, and
just the question, I mean, you're averaging over the whole hysteresis loop, or you're doing it at a specific point?
We average over all, and we also looked at windows close to crossing the crossing the zero magnetization. So for all statistics, we had the same result. So it was not.
Same exponent.
Yeah. So so here, correct me if I'm wrong here. So previous work of Pierre and collaborators looked at avalanche and equilibrium of the SK model, and they found remarkable similarities with the results found in avalanches out of equilibrium of the SK model. So they found similar exponents or equal exponents for equilibrium avalanches as for out of equilibrium avalanche, as the one I showed you before, and also extended this work to using some problem arguments in equilibrium avalanches for three-dimensional Edward Anderson spin glass. So what we wanted to test if these similarities found in equilibrium and non-equilibrium avalanches would hold also for the Edward Anderson spin glass. So we looked at the three-dimensional Edward Anderson spin glass in the same way as the SK model, and here I show you the distribution of spin flips for the Edward Anderson model in 3 dimensions. So we went to very, very large system sizes. So these are over 10 million spins. And we see here that there is really no signs of scale-free behavior. So even having such a huge, large systems, the avalanches are bounded up to a couple of hundred spins. So we see no signs of scale-free behavior. So what
is D of n?
Units is the frequency of avalanches having, let's say, one spin flip.
So how do you trigger this? I don't understand.
The avalanches are triggered in the same way as shown here. So you start with a fully magnetized system, and then so you apply a field that is strong enough that all spins, in this case, okay, just the other way, are pointing down, and then you choose a magnetic field where just one spin becomes unstable and can flip, and then you relax the system, and then you find again the next field that destabilizes the next spin, and then so on. And we find no signs of self-organization.
In both cases, you just consider a spin flip.
Yes, just one spin. Yeah. So we asked ourselves if maybe it could be some feature of mean field of the SK being in another universality class of the Edward Anderson model, and then we went to the critical dimension 6 to see what happens there. So now again we run simulations for very large system sizes, and we see again no signs of scale-free behavior. So we see that here sizes are not the largest avalanche size is not larger than also again a couple of hundred, but it has some. It's a bit larger, so it has some trends. So we go deep into the, let's say, universality class of the mean field universality class. We go to 8 dimensions. Again, these are huge system sizes, and we see again no signs of scale-free behavior. So we're puzzled and to understand what's happening here. So why in the S scale we find this very interesting behavior of self-organized criticality, and the infinite dimensional we don't find any. So we did this analysis again of the characteristic avalanche size. So
isn't this to be expected? I mean, if you have finite range interaction, if you have an infinite interaction, it's clear that probably the whole system will be affected. But so is this a big surprise?
Well,
The avalanche in ferromagnets.
That there is a big difference between the ferromagnetic
Yeah,
and
sure,
the
sure.
Okay.
So just a one question. So this scale is getting bigger and bigger with dimension increase, but so the slope.
Here, so here we
is very close to 1.
so here was really difficult to. So we probably it's close to 1, but so especially though for here was difficult to really find a power law, but here we did not look very careful at the power law because it was still not very easy to find which is the right fit. But what we do is we start we do this characteristic avalanche size for each dimension, and we plot it as a function of the dimensionality. So we find here we plot 1 over n star as a function of 1 over d square, and here we estimate this characteristic avalanche size for 2 dimensions, 3 dimensions, 4 dimensions, and then so on, and find a clear relation, and we see that we will find scale-free behavior only in the case when we have here infinite in the limit of infinite dimensions. So so far we wanted to understand which can be the properties of the SK model that drive this system that display self-organized criticality. So is it the long-range nature of the SK model as previously said, or is it the diverging number of neighbors? So what is the one of these the property that is relevant? So far we have used so the coordination number of the system was directly coupled to the dimensionality, such that when we made the extrapolation to infinity, it was the coordination number of the system also went to infinity. So we wanted to test a system that lives in an infinite dimensional space, but with a constant number of neighbors. So and this model is the Viana-Bray model. So this is a model that has here random coupling. So it can have it has random couplings, and each spin has a fixed number of neighbors, but this number of neighbors can be just randomly picked. So it's in this sense a very long-range interaction, but you just control the coordination number. And we wanted to see if we find here some signs of self or scale-free behavior. And again, here we see that there is no apparent scale-free behavior. So from this, we came to a conclusion. So maybe a condition for self-organized criticality is to have a diverging number of neighbors in the thermodynamic limit in disordered spin model.
And your data were for which Z?
These were for 6.
Has this been done on the beta lattice too?
No, we did not try that. So far, we wanted to look further for models that could be candidates to show this interesting behavior of self-organized criticality. And one of these models with these candidates was the Coulomb glass. So this is a model that describes systems that with strongly localized electrons and unscreened Coulomb interactions. And it also shares some similarities with the SK model, and so it was a good candidate to test for avalanches. So here, this is the Hamiltonian of the Coulomb glass model. So here is the charge. So we can set it to 1, the position of each of the charges, and I and j are the occupation number, and 1/2 means that the system is half filled, so that we have half of the sites are occupied by an electron and others are empty, such that the system has a charge neutral system. Here the disorder comes into the system by random potentials, and the system can be driven out of equilibrium by an external electric field. The good thing is that we can map this model to a spin model, but with the condition that we have magnetization conserving dynamics. So this will guarantee that we will have a particle conservation and that the system will stay charge neutral.
And the Aij are 1 over the distance.
Yes. And so we wanted to look at this system and then apply an external electric field and see what happens. So we prepared samples that are close to the ground state and then applied slowly an electric field. So here's how we did. So here we have here the electrons and with their random potentials, and we apply a field that destabilizes one electron just enough to jump to one of the empty sites. By doing this jump, it can trigger other electron hops. So we measure the total electron hop and the net charge displacement. And so what we find here is, so for fields, for small fields, we find that there are just one hop, so just one electron rearrangement, so nothing really interesting. If we increase the field, there are some hops that have 2 electron hops, but again, nothing interesting. And
so what's the initial condition?
We go to states that are close to the ground state, so we cannot really prepare ground state, but so we try to drive in, so to put them in pseudo ground states. And as we increase the field, we see slowly a size dependence emerging and some kind of power law. And when we increase even more the field, close to the pinning field, where we just have a continuous current, some scale-free behavior seems to emerge. So we again use the same analysis with a characteristic avalanche size defined before to see if we find here scale-free avalanches. And just for fields that are close to the pinning field, we see that the avalanche become infinite in the thermodynamic limit. So far we have seen that that in this case we don't see self-organized criticality, but scale-free behavior just close to a specific critical field.
Could it be that the distance to the critical field somehow determines a correlation length, and that your maximum avalanche size is given by this correlation length which diverges at the depending transition?
Yeah. So. Yeah, that can be.
This would be natural, I think.
Yes, that would be. Yeah, we were just. I think that's. So we were just wondering if we would see something interesting, not at the critical field, but so not having to tune anything, and to see if we would see something.
But you could check this if you go closer and closer to the depending transition. You could check this from your avalanche size, I think.
Yeah. Okay. Then we have to check that, but no, we didn't.
So you're saying there are infinite avalanche already, very large avalanche already in the finite range.
Sorry, I guess.
In this whole range of field, there are very large avalanche.
Yeah. So
in how many dimensions was this?
Sorry.
How many dimensions?
The 3-dimensional Coulomb. Yeah. So far we have seen avalanches of self-organized criticality in spin glasses when the number of neighbors diverge, and specifically we here had single flip dynamics, and then we looked at a different system with diverging number of neighbors, but with magnetization conserving dynamics, and we see just scale-free avalanches close to a specific.
What do you mean closer means? At the beginning, or?
No, it was also when being just close, so it was not at the beginning exactly. So.
I think it's okay to take an interval around the critical point. That's fine. It should be. Yeah, makes sense.
Yeah. So otherwise, it was really. So.
Can I ask one other question on the first part, the SOC? When you did 8 dimensions, you had a finite cutoff, right? Did you have a power law part to it too before you got the cutoff, and did that power law sort of agree with what you saw in
So it seems like that, but it was not so easy to really see if to fit a power law there. So it was a bit hard. So maybe at higher dimension that could be the case.
So if you like tuned the width of the distribution of couplings, for example, did the cutoff change? Did you check that?
The width of the no. We did not check that.
Okay.
No.
Okay.
Of course, so we came just now to see which are possible differences between the systems that might be responsible for this difference. For in one case having self-organized criticality and another not. So of course there are other differences in the model, so they're quite different, but still one of these differences might be the dynamics imposed into the system. Since conserving magnetization conserving dynamics make that the system cannot really explore the whole configuration space that might be possible, but it just lives on a subspace of it that may inhibit the spreading of very large avalanches. So the question here is if this could be due to different dynamics applied to the system. So I will now show you. So work in progress that we have. So we are now interested in trying to find out if dynamics could influence and the presence of or absence of self-organized criticality. And where we're looking now is to see in a single flip dynamics to study a diluted dipolar system, which is known to have a spin glass phase below a dilution, and then do the same procedure as for the SK, apply a very strong magnetic field and see if we find avalanches. It would be a system that is finite dimensional but has a infinite number of neighbors in the thermodynamic limits because of the long range interactions. And then we can look at magnetic conserving dynamics in the SK model, where we know there is self-organized criticality, and apply an alternating field and just see if we find there a self-organized criticality or scale-free behavior. And by doing so, we think that we will be able to answer the question if the dynamics play a role or not. So this is still in progress, and I hope to have concrete results soon. But I will be very happy to get any input about this work in progress. Okay. So that's all. Thank you.
Thank you very much. Questions? No questions?
Well, I think a key point here it would be to include also many electron jumps, because that's what would really drive self-criticality.
Well, yes, that's very hard numerically, but yeah, that might be. But yeah, so it becomes really, really hard.
Yeah.
So in all of these, you kept the width of the distribution of the couplings the same. Right?
Yeah.
Yeah. I think it might be interesting to see if that.
To see, so we don't expect to see many difference because it will just have another energy, so other energy scale.
I see.
But,
Really? I mean, I know for the random field, if you tune the disorder, if you're not at the critical disorder, you don't see power law, and only at the critical disorder you see. So here you're saying it's just a rescaling factor or something?
Yes.
It's different.
Yeah, I think it's a bit different with the spin glass and the random field.
I see.
Random field, you have the newest neighbor, which is ferromagnetic.
Well, yeah, that
so you
too.
have to compete.
Yeah, no, that too. I agree. But
But yeah, so that should be also straightforward to check, but we don't keep on.
Okay.
Just a naive question. You have these hysteresis, and you basically have avalanches in different parts of these hysteresis, and you, when you compute the distribution, you average over whole hysteresis, or you take some. Why the distribution of avalanches should be the same in different parts?
So we looked at different ranges. So we we also tried just to see in a window of the hysteresis loop, but there we did not see any difference.
So there is no any difference.
No.
Any questions? Okay, so we can start.